Welcome to the deep dive. Ever wondered just how strong those cool things coming off your 3D printer really are?
Yeah, it's a good question.
Today we're diving into a fascinating study that really put a popular 3D printing plastic called PETG to the test,
Right.
specifically looking at how its internal structure and those outer layers affect its strength when you try to pull it apart or slide its layers,
Yeah,
tension and shear.
exactly. And we're talking about parts made with a really common method, Fused Deposition Modeling, or FDM.
FDM.
This research really gets into the weeds of how the way the plastic strands are laid down inside, that's the raster orientation, kind of like the grain in wood, you could say,
Okay, like wood grain.
and whether or not it has that smooth outer shell, the contour, how all that influences how much stress these parts can actually handle.
And they didn't just test it, they tried to predict it too, with some kind of model.
That's right. Importantly, they also looked at whether a standard engineering model, the Tsai Hill criterion, could accurately predict this strength. So if you're using 3D printing for anything beyond just, looks, maybe you're making tools or brackets, functional parts that need to hold up,
Yeah, stuff that needs to work.
then this is definitely something you want to hear about.
Okay, so let's unpack this FDM process first. For those of us who maybe just hit print, what's the essential idea? How does it build these parts, especially in the way this study looked at it?
Okay, think of it like building something with tiny, really precise hot glue strands.
Right.
The printer takes a spool of solid plastic filament, in this case, PETG, and feeds it into a heated nozzle.
Melt it down.
Exactly, melts the plastic, and then the nozzle moves around, squeezing out these thin, molten lines, layer by layer, just following the digital design.
Layer by layer.
Okay. Now, this study was super precise about it. They used a specific Prusa printer, a March 0.2 millimeter nozzle, which is pretty fine,
Yeah.
and they carefully controlled the temperatures. The nozzle was at 230 degrees Celsius to melt the PETG properly, and the print bed, where the part is built, was heated to 80 Celsius. That helps the layers stick together well.
Gotcha. So it's all about laying down those hot plastic lines just right. And the study really focused on two main things about how they laid those lines, didn't they?
Exactly.
The direction inside the part, the raster orientation, and whether it had that extra outer skin, the contour.
Precisely. Raster orientation is all about which way those melted plastic filaments are pointing within each layer.
Okay.
Like you said, the grain. Imagine the planks in a wooden floor. That's sort of the idea. This study tested three main directions relative to where they were going to apply the force later on.
Right. What were they?
Straight along the direction of force, that's 0 degrees, then crisscrossed at angles, plus and minus 45 degrees, and finally perpendicular to the course, so 90 degrees.
0, 45, 90. Makes sense.
And they also made sure the inside of each part was completely solid, what's called 100% infill. That's key for ensuring good connections, good adhesion between the layers.
No gaps inside.
Right. Then they compared parts made like that with and without a contour. The contour is like adding a couple of extra very thin outer layers. It gives a smoother finish and, as we'll see, potentially adds more strength.
Okay, so different internal grain directions and with or without that smooth outer finish.
Got it. So how do they actually test the strength? Let's start with pulling them apart, the tensile tests.
Right, tensile testing. They use a standard method for this. It's called ISO 527-2.
Okay.
Think of it like a high-tech tug-of-war with a carefully shaped piece of the 3D printed plastic. They clamp the ends into a machine and pull it steadily until it breaks. All the while, they're measuring exactly how much force it takes and how much the material stretches or deforms before it finally snaps.
And the interesting part is how those different print directions behaved.
Oh, definitely. Really different results depending on that raster orientation.
All right, let's hear it. What happened in the tug-of-war? Which grain held up best? Well, no huge surprise maybe, but when the internal lines, the filaments, were running straight along the direction they were pulling, that 0 degree orientation,
Yeah.
those parts had the highest overall tensile strength. They could take the most pulling force.
Okay, strongest along the grain.
Yeah.
Did the contour, that outer shell, help there?
Interestingly, for that 0 degree pull, adding the contour didn't make a huge difference in the maximum force they could withstand. But there was a difference in how they failed. The parts without the contour didn't stretch quite as much before breaking. They were a bit more brittle in that sense.
Less stretchy.
Right. But they could actually absorb more total energy before they fractured. So kind of brittle, but tough in terms of energy absorption.
Oh, okay. So strongest along the grain, Shell doesn't add much to peak strength there.
Hmm.
What about turning the grain sideways when the lines were at 90 degrees to the pole?
Yeah, the 90-degree case. So when those internal filaments were at a right angle to the pulling force, well, those parts were still stronger than the 45-degree ones we'll get to. But they failed much more suddenly, a real brittle failure. You could see cracks just zipping straight through the layers.
Well, like,
And the ones without the outer shell, they actually had the lowest fracture energy of all the samples they tested in tension. It's like the layers were just peeling apart.
right, like trying to pull apart a stack of paper from the edge. Not strong that way.
Exactly. Imagine trying to snap a deck of cards in half by pulling on the short edge. That's kind of the failure mode you're seeing. The bond between layers is the weak point there.
Ouch. Okay, so pulling across the layers is definitely a weak spot. And then there was the middle one, that 45-degree crisscross pattern. How did that do in the tug-of-war?
The 45-degree orientation. This one actually had the lowest tensile strength.
Lowest.
Yeah, lowest peak strength when they pulled on it, whether it had the contour or not. However, and this is a really key difference, these parts were much more ductile, more flexible.
I stretched more.
A lot more. They stretched quite a bit, showed significant elongation before they finally cracked and broke.
Interesting. And did the contour help here?
Yes, definitely. In this 45-degree case, that outer contour made a noticeable improvement. It increased both the maximum strength they could handle and how much energy they could absorb before breaking.
So it toughened them up.
It seems like it. It's likely that the contour helped sort of constrain those angled layers, held them together better, and stopped them from peeling apart quite so easily.
Makes sense.
The study even has pictures, figure 5, I think, that really show these different failure modes. You can visually see how differently they broke based on that internal structure. It's pretty clear.
Seeing is believing, for sure. Now, you mentioned they measured stretch. The study used some fancy tech for that too, right? Something. Digital image correlation.
Yes, exactly. They used 2 methods, actually. One was a standard mechanical extensometer, basically a little clip-on device that physically measures how much the part stretches between 2 points.
Okay, the standard way.
Right. But they also used digital image correlation, or DIC. This is a really neat optical technique. You spray a random black and white speckle pattern onto the surface of the sample.
Like a random dots.
Yeah, just a random pattern. Then you use cameras, usually 2, for 3D measurements to watch that pattern as the material is pulled or deformed.
And the computer tracks the dots moving.
Precisely. Software tracks how those speckles move and distort, and from that, it can calculate the strain, the amount of stretch, across the entire surface, not just between 2 points.
That sounds much more detailed. How did it compare to the clip-on thing?
They found the results from the 2 methods generally agreed well, which is good validation.
Okay.
But the DIC was particularly useful because it could show where the strain was concentrating, especially in areas where maybe cracks were starting to form or the stretching wasn't perfectly uniform across the whole sample. It gives you a full field map of the deformation.
Very cool. Okay, so we've got pulling apart covered tension. But the study also looked at shear forces, right? That kind of sliding, twisting stress.
That's right. Shear's a whole different ballgame.
How did they test that? And what did they find there?
For the shear tests, they had to use a different shape of sample designed specifically for shear, and they followed another set of standards, ASTM D5379, I believe it was, or maybe a variant like 831.5 for thin plates. The idea is to apply force in a way that tries to make the layers slide past each other within a specific zone.
Okay, forcing that sliding motion.
Exactly. And again, they tested the same 3 internal grain directions, 0, 90, and 45 degrees, both with and without that outer contour shell.
And did the results mirror the tension tests, or was it different?
Quite different in some key ways. The contour, for example, seemed to play an even bigger role in some of the shear tests.
So interesting. Okay, let's hear it. What happened when they tried to make the layers slide?
All right, so for the 0-degree orientation where the internal print lines were running along the direction of the shear force, the parts without the outer contour performed pretty poorly.
Why is that?
Well, because those filaments were already lined up in the direction the force was trying to make them slide, there wasn't much inherent resistance to that movement within the layers themselves. The failure really depended on how well the layers stuck to each other.
Okay. But what about with the contour?
Adding that outer contour made a big difference for those 0-degree parts under shear. That outer shell acted like a reinforcement, really enhanced the performance, and helped prevent those layers from just sliding apart too easily.
So the shell was key there.
It really seemed to be. They saw the cracks starting within the specific area designed for the shear test propagating through the layers.
Okay, so for shear, that contour was a real game changer for the 0-degree alignment. What about the other directions, 90 and 45?
The 90-degree parts where the lines were perpendicular to the shear force, they showed quite a lot of deformation, sort of bending and squishing in that test area,
Yeah.
until eventually the adhesion between the layers failed. The cracks tended to form horizontally right along those layer lines, which makes sense.
Again, layer bonding being critical.
Exactly. And interestingly, they didn't stretch or deform as much overall before failing compared to the other orientations in shear lower strain values observed.
And the 45-degree, how did that do under shear?
Now, the 45-degree orientation, the crisscross pattern, this one really stood out in the shear tests. It actually showed superior performance.
Better than 0 and 90.
Yes, higher shear strength and also higher toughness. It could withstand more deformation before breaking compared to the others. The strain, according to the DIC they could get, was nicely concentrated in that calibrated shear area.
Okay.
And when it did fail, the cracks tended to follow the plus-minus 45-degree angle of those internal printed lines.
Fascinating. So it's like the angle structure was better at handling that sliding force.
It seems so. That interlocking pattern provided more resistance to the layers sliding past each other, and figure 12 in the study apparently shows these different shear failure patterns quite well.
It's really amazing how the failure mode changes so much depending on the force in the prim structure. And it sounds like for shear forces, generally speaking, adding that contour is a good idea.
Absolutely. That was a clear takeaway from the shear tests. The study really emphasized that the contour significantly enhanced the shear strength and toughness across most of the orientations they looked at.
Good to know.
They did mention, as a side note, that getting good DIC images for all the shear specimens was a bit challenging, maybe due to the complex deformation or image quality.
Right.
But the overall trends in terms of strength and failure modes were pretty clear from the mechanical testing data.
Okay, so we've got a good handle now on how these PETG parts behave under pull and shear based on how they're printed. Now, let's circle back to that engineering model you mentioned earlier, the Tsai Hill failure criterion.
Yes, Tsai Hill.
What exactly is it, and why bring it into this study?
Okay, so the Tsai Hill criterion is basically a mathematical tool, an equation that engineers use to predict when a material will fail under combined stresses. It's particularly useful for materials that aren't equally strong in all directions, what we call anisotropic materials.
Like our 3D prints with their grain.
Exactly like our 3D prints. Because of the way the layers and filaments are laid down, the part is stronger along the filament direction than perpendicular to it, or maybe compared to shear. Tsai Hill takes these different strengths into account.
So how did they use it here?
What the researchers did was clever. They took the strength values they actually measured in some of the simpler tests specifically, the tensile strength at 0 degrees, the tensile strength at 90 degrees, and the shear strength measured on the 45-degree samples, and they plugged those numbers into the Tsai Hill equation to try and predict what the tensile strength would be at that trickier 45-degree angle.
Oh, okay. So use easy measurements to predict a harder one.
You got it. So if you're designing a part and you know it's going to see stress mainly at a 45-degree angle to your print lines, you could potentially run these other, perhaps easier, tests, 0, 90 tensile, 45 shear, and use Tsai Hill to estimate how strong your part will be in that 45-degree direction without having to test that specific angle every single time.
That sounds incredibly useful for design work. So the big question, how well did the predictions match up? Did the model work?
The predictions were actually remarkably good, surprisingly accurate, I'd say. Yeah, especially for the parts without that outer contour. Let's look at the numbers. For the 45-degree parts that did have the contour, the Tsai Hill model predicted a tensile strength of about 53 megapascals, 52.95 to be precise, and what they actually measured in the lab was 51.1 megapascals.
That's pretty close. What's the error?
Only about a 3.5% difference, which is quite good in material science terms.
Okay, not bad at all.
Yeah.
What about without the contour?
Even better. For the 45-degree parts without the contour, the model predicted 48.9 megapascals. The experimental measurement, 48.62 megapascals.
Why,
That's an error of just 0.6%. Extremely close.
That's almost dead on. So why was it slightly less accurate for the parts with the contour? Any ideas?
The researchers suggested a reason for that slightly higher error in the contoured specimens. They think it might be because that outer contour shell itself has its own filament orientation, right?
Yeah, it's printed too.
And where they performed the shear test, which is one of the inputs for the Tsai Hill model, the orientation of the filaments in the shell might be slightly different from the main internal 45-degree structure in that specific shear zone.
Ah, so the shell adds a little complexity that the basic model doesn't perfectly capture for that specific input.
That seems to be the hypothesis. That slight difference in how the material is actually oriented right there in the shear test area could introduce a little bit more variation between the prediction and the reality for the overall 45-degree tensile strength.
That makes a lot of sense. Okay, so let's go and bring this all together. We've covered a lot of ground. What are the really key takeaways we should remember from this deep dive into 3D printed PETG strength?
Yeah, I think there are a few really practical points here. First off, pretty clearly, if you need maximum tensile strength, pulling strength, align your print lines with the direction of that force. That 0-degree orientation is your strongest bet.
Okay, rule 1, align with the force for tension.
Rule 2, maybe? Adding that outer shell, the contour, seems to be generally beneficial. It tends to improve both tensile and shear strength, and also the toughness, how much energy the part absorbs before breaking.
You said tougher overall.
Yeah, it seems to enhance the layer adhesion and provide some extra structural confinement. So unless there's a strong reason not to, using a contour looks like a good idea for mechanical parts.
Good default setting, maybe?
Perhaps. And third, it's really encouraging to see that established engineering models, like the Tsai Hill criterion, can be quite accurate in predicting the tensile strength of these FDM parts, especially for the simpler, uncontoured structures. That's valuable for design.
Yeah, predictive power is huge.
Definitely. And finally, the utility of tools like DIC, it really gives us a much richer picture of how these materials actually deform and fail under stress, especially for complex tests like shear, where a simple extensometer might not tell the whole story.
So wrapping it up, if you're designing something in PETG, know it's going to be pulled hard in one direction, line up those print lines, the raster with the force. That's job 1.
Absolutely.
And adding that contour seems like a good insurance policy for just better overall strength and durability, especially against shear. Plus, it's cool that we can actually predict this stuff with reasonable accuracy using engineering math.
Exactly. This kind of research provides really practical, actionable knowledge for anyone pushing the boundaries of FDM 3D printing beyond just making models moving into functional parts. Understanding how these fairly basic print settings impact mechanical performance, well, it lets you make smarter design choices.
And get more reliable prints in the end.
That's the goal.
Well, this has been a truly eye-opening deep dive. It's amazing how much difference the internal structure and even just a couple of extra outer layers can make to how these parts hold up.
It really is. The details matter.
So for you, the listener, here's something to think about. How could knowing about raster orientation and contours change the way you approach your own 3D printing projects? Could you design stronger, more reliable parts just by tweaking these settings? And what other properties, maybe beyond just strength, might be worth exploring in future research on these FDM materials? Lots to ponder there. Thanks for joining us on the deep dive.